Hello everybody and welcome to this module on deformation gradient. So in this module, we're going to basically get into the general form of the deformation gradients or the large deformations. So far we discussed the infinitesimal strain tensor and now we're getting back to the deformation gradient. So if you remember, we developed some kind of uh, you know relations base for the deformation gradient. If you recall, where we called it f, it was a tensor, a transformation tensor, which transform our reference configuration to the current configuration. And then from here we extracted e was the large deformation or the general deformation, general strain tensor, or we call it the green Lagrange strain tensor. From here, we extracted under some assumptions and just disregarding the nonlinear part, the E star or the Cauchy strain tensor. And then now, by discussing this, we are focusing on this again and the large deformation gradient. And before getting into the general form of the deformation gradient, the book actually brought two topics, two very simple deformation gradients: local rigid body motion and pure stretch. Next, after discussing these two very simple deformation gradients, we're going into the polar decomposition and the general deformation gradients and large deformations. All right, so let's get to the deformation gradient. So if you recall, we had this reference configuration in here. So we had this reference configuration, and then we had this as the current configuration. We had a local coordinate system, x1 and x2. And if you recall, we had this point P T0, and this one was Q T0. And there were, counterparts points in current configuration as P, T, and QT. Then we had these vectors, if you recall this was x, this was x, capital X, this was small x, and then we had d small x, we had d capital X, and then we had our displacements u x and ux plus delta x. Let me just write all of them in here. So we had this capital X, we had this as small x, we had this as d capital X, and this was d small x. This was u, x, and t. And this was u, x plus dx and t. So if you remember, we said that here for the current configuration, we had dx was equal to x at q, which was x of x plus dx and t, minus this x at point P. So we have this vector, small x, becomes x of capital X and t, where we said that this is equal to, so if I divide this by dx, d capital X, this becomes the gradient of x. So del x d capital X. And here, del x is of course equal to, so maybe I bring it a bit down. Oops. So it was the partial derivative of x1 with respect to capital X1, capital X, small x1 with respect to capital X2, x1 with respect to capital X3. And it was this tensor in here where we can call this as dx is equal to f dx, where f is equal to del x. So this is one format of writing the large deformations in form of displacement. In form of material coordinate del x, and del x is this tensor, this second order tensor in here. We also had another way of writing this. If you recall, we said that dx is equal to, this is dx is equal to x plus u. X is basically capital X plus u, x, and t. And x plus dx was x plus d capital X plus this u in here. So it was x plus dx is equal to x plus d capital X plus u, x plus dx and t. And if we subtract the lower from the upper, then we got dx was equal to, this would go with this one with this one, get dx plus u of x plus dx and t minus u, x, and t. And we already said that if you divide this by d capital X, then this is the gradient of u. So dx becomes dx plus del u dx. And we said we can write this as di plus del u dx. This is also another representation of the finite deformation. So far, we just saw these two deformations in here. We also call this as f, right? Because it is also a second order tensor, which transforms your recurrent configuration to the reference. And also if you put f inverse in here, then you get your current configuration to the reference configuration. All right. There are so many other kind of, tensors where you can use accordingly based on your, your application, which way or approach you utilize to solve a problem. In the next chapter, we will see that we have different kind of, for example, stress tensors, stress transformation that you can utilize based on your, your current, whether you're in the current configuration or in the reference configuration, to find the transform stress, to find the transform stress in the initial, in the reference, and the current configuration. We have Cauchy strain, we have the Pula-Kirchhoff strains, and so many others, which you can learn from other papers or books. Here we have the same strategy. So we have different representations for the large deformations in here. This is based on displacement, and this one is based on the material coordinate. All right. So with this in mind, we're going to pinpoint two important properties. So the first one is that this transformation matrix, where we call this F, for example, or this F in here, it is always inversible. So suppose you have dx equal to f d capital X, and this f could be del x, or it could be I plus del u. It is not important which one you choose. You can write f inverse dx is equal to dx, because you know f inverse f is I, so I don't write it, just remove it from here. So you can move from your current configuration, so you can move from your reference configuration to the current, and also from the current to the reference configuration. This is the first one. So I can write it as this. So there's this transformation of each, let's say, node or particle from reference to current configuration and vice versa. Therefore, F inverse exists. This is very, very important. So you can switch between the current and reference configuration. Another important thing is that when you have something in the reference configuration, so suppose you have a particle in reference configuration, and your reference configuration here, we make this assumption that it follows the right-hand rule. So it is E1, E2, therefore E3 is in this direction. Therefore, if you have that particle again in, I don't know, in the current configuration, then you again have this right-hand rule again here. So it is not something like E1, E2, and then E3 becomes this one. This is impossible. So you can't do this, because otherwise your the determinant of your transformation matrix of your transformation tensor, this F, becomes negative. And this is something that we don't want it. You might have heard of, Jacobian matrix in the finite element course, where we said that we would like to have the Jacobian to be positive. So the determinant of Jacobian to be positive and very close to 1. So you don't want your element or your particle to be very, very distorted. It's because you want it to be close to 1, and also you want it, sorry, it should be bigger than 0. So you want it to be close to 1 because you don't want it to be, for example, distorted like this, something like this. So you want it to be distorted like this, for example. And the Jacobian should be positive, because you don't want it, because otherwise this point, for example, here, it does not exist in the reference, in the current configuration, if your Jacobian is is less than 0, is negative. So we always want our deformation to follow the kind of configuration we had in the reference configuration. Let me just write this here. So for this one, we need to have the determinant of f larger than 0 to be positive. All right, so when the reference sorry, when the reference configuration is deformed, it deforms such that the initial unit vectors elongates and rotates. Elongate and rotate. If we have E1 dot, for example, E2 cross E3, which is equal to E2 dot E3 cross E1, which is equal to E3 dot E1 cross E2, then it remains the same in the current configuration. Therefore, for the transformation, maybe it's better for the transformation f e1 dot f e2 cross f e3 is equal to f e2 dot f e3 cross f e1 is equal to f e3 dot f e1 cross f e2, which is equal to the determinant of f is always positive. All right, so now we mentioned two important properties for the transformation matrix F. So the F inverse actually exists, and also if you have a right hand row, if you have a right hand unit vectors in your reference configuration, it remains the same in your current configuration. So let's see what happens if if the determinant is negative. So as I already said, if the determinant of f is less than 0, then it shows that the particle does not exist in the current configuration. This is the same that I already mentioned about the Jacobian. Jacobian is nothing but this del x in your finite element course. It is this kind of representation of the deformation. So that's why we say that we don't want the Jacobian to be negative. Therefore, it won't exist in the current configuration. If the determinant of f is less than 0 or negative, then we cannot cannot simply, sorry, move back to from current configuration to the reference. Why? Because I already mentioned the particle does not exist. Remember, the book also put this in to a footprint that we use the right hand sided basis. All right, and here we make this assumption. It's better to write it here. So we use right handed basis. Great. All right. So now we know two important properties of the deformation gradient. So now let's get to some special forms, very, very special and simple forms of the deformation gradient. So the first one is local rigid body motion. So before getting into this kind of spatial transformation, let's see what it decomposes of. It decomposes of two important, parts. For the first one is local, and the second one is rigid body motion. So the first indicates that we are dealing with a particle in a continuum where it is surrounded by an infinite number of particles, so it is local. And the second one says that it is rigid body motion, so you don't have any deformation. It is just, rotation. So if you have your current configuration like this, so it will rotate like this. So with this in mind, then we know that we have a local rigid body motion. So neither length nor angle of the element are changed. So we only have rotation. So the determinant of f is also positive, and f inverse exists. We already mentioned this. Also, we have f transpose, because this is rotation, an orthogonal kind of tensor, rotation tensor. So f transpose is equal to I. The determinant is equal to 1. And determinant of f is equal to 1. The book actually brought an example like 1, 0, 0, minus 1, 1. So you see that the determinant is 1, and also f transpose is I. This is a local rigid body motion. The next spatial case is pure stretch or pure stretching deformation, where it says that if you have so pure stretch is a deformation tensor, that is positive definite. What does it mean? So it means that for each vector A, you have A dot UA larger or equal to 0, where this U is the pure stretch tensor or pure stretch deformation tensor. So it can be shown that if you have a positive definite tensor like this, if a tensor is positive definite and of course symmetric, where is the case for our problem, then it has then all of its eigenvalues are positive. So now we get why we call this stretching tensor. So it is like, you can think of it like if you have an element like this or a particle like this, it deforms like this. So it stretches like this. So you can write U. So if we rewrite U in the form of its eigenvalues, then we have U equal to lambda 1, lambda 2, lambda 3, where they are all positive. We get something like this. So we have dx is equal to f d capital X, and now we replace this f with u. It's a special case of f. So if we have this, so we get, just move this one line down. So we get dx1, dx2, dx3. Then we have lambda 1, lambda 2, and lambda 3, and the rest are 0. And then we have dx1, dx2, and dx3. So this become dx1, dx2, dx3. This is equal to lambda 1, dx1, lambda 2, dx2, lambda 3, dx3. Therefore, you can see that lambda 1 is basically dx1, the dimension of dx1 divided by d capital X1. Lambda 2 is dx2 divided by d capital X2, and lambda 3 is dx3 divided by dx3. And now you can see that how your reference, your particle in the reference configuration is basically stretching in the current configuration. This is lambda 1, lambda 2, and lambda 3. So it deforms like this. As I already mentioned, if you have a particle like this, it will stretch like this. There is a very nice kind of example, I guess, 3.20.2. This will show how this, this stretching, this pure stretch kind of tensor actually works. We switch to Maple to also get a very nice visual illustration of this transformation matrix.
All right, so here we are with the example 3.20.2. So here I restart everything and I import some necessary tools in here. So the initial sphere equation that we had in the problem is this one. So if we solve this for z and I plot this in 3D for both the solutions, I mean here I have solution, the first one, this is the first one, and this is the second part of the solution. So here I plot the first part of the solution, sol1, and here I plot the second part, and here I show both of them. So as you see, we have a sphere here where the upper represents solution 1 and the lower represents solution 2. So if you want to have a better idea, you can just remove this colon here. So you see that here we have the lower half. All right. So after doing this, we are going to the deform spherical equation here, sphere equation. So here we have 3 lambdas, which are the eigenvalues of the transformation, 3, 4, and 1. And I also included the stretched sphere equation here. So you can see something like this, equation number 3. And if we solve this stretch sphere equation for z, we get 2 equations here, and similar to above, I plot the first upper and lower half, and if you plot, if you put together the both sides, you get that this is the stretching sphere, like the one that you saw in the book. So here the pure stretch deformation tensor has been utilized to see how this sphere is deformed into a kind of stretching sphere.